So hello, my name is Parth Purivan, and this is a channel regarding mathematical questions. And this is a mathematical question from a YouTube channel named Young Mathematician. And the person who is running this channel is actually a small kid who is solving really tough mathematical question, which I admire because at his age, I was just drinking fruity and doing nothing. There was a video of him solving this definite integral question, which you can see in this video also, and the way he had solved is actually wrong and actually wrong, and it is also very complicated. Okay, so I should not advise anyone to solve that way. But he's about 10 to 12 years old, and I should really appreciate that he actually know what the heck is this infinity sign. But I have tagged him, and I just want him to see this video regarding the correct solution of this integral question, or nice and a clear solution to this question. So here we go. So first of all, we need to solve this question having from integration from 0 to infinity of natural logarithm from ex plus 1 divided by ex minus 1 dx. So the solution begins right now. So first of all, we will basically going to consider ex plus 1 divided by ex minus 1 is equals to t. And then we will basically going to take ex minus 1, which is in the left hand side denominator, and we will basically going to take this to the right hand side numerator part. So ex minus 1 will be multiplied with t, and so we will basically going to get our second step. Then what we will going to do, we will basically going to differentiate both the sides. Okay, so we have put d on both the sides, and using the rules associated with differentiation, I have first differentiate ex, and then I have differentiated 1. As we all know that 1 is a constant, so the differentiation of any constant is just 0, and the differentiation of ex is just ex. So d of ex is ex dx. And I have used the product rule of derivatives to evaluate t into ex, which has landed me t times of ex dx plus ex and the derivative of dt multiplied with it. And the derivative of t is just t, because t and x, both of them are variables. It is eventually that t is also variable because it is being connected to another variable x. Now, rearranging the third step, or rearranging this step, I have come to this, that I will basically going to take this t times of e to the power of x dx into the left hand side. So I will basically going to get to my fourth step, in which there is ex into 1 minus t dx, which is equals to ex minus 1 dt. All right. Now I can represent dx as ex minus 1 divided by ex. I will going to take this ex in the denominator, and so 1 minus t also in the denominator. So this is the final expression which I had come with. Now I need to make this ex, or I need to make this right hand side of this expression in the form of t only. Okay, so I need to convert this ex into something t, and I have considered ex plus 1 divided by ex minus 1 as t. So I can use this expression to find the value of ex in terms of t. Now you can simply do it. It is not that big deal. There's a rule called Copenindo and dividendo rule in which we can directly do this thing. It is just that we need to add the denominator. We need to add the denominator and the numerator in the numerator, and we need to subtract the denominator from the numerator in the denominator on both the sides. Okay, which I represented. In this side, the denominator is 1 in the side of t. So by resolving ex plus 1 divided by ex minus 1 is equals to t, and need to find the expression of ex in terms of t, I've arrived that ex is equals to t plus 1 divided by t minus 1. So putting this expression of ex in terms of t in this expression of dx, I've arrived to a value of dx in terms of t, which is 2 divided by 1 minus t square into dt. Now, one thing we need to take here, that now you can see the full screen, that as x is approaching to 0, and as we all know that t is equals to ex plus 1 divided by ex minus 1, so ex will be approaching to 1 when x is approaching to 0. So ex plus 1 divided by ex minus 1 will be approaching to 1 divided by 0. Sorry, it will be approaching to 2 divided by 0, which is infinity. So we can directly tell that when x will be approaching to 0, t will be approaching to positive infinity. Okay, because in the numerator we are having a positive number. Similarly, when x will be approaching to infinity, as you can see here, when x is approaching to infinity, then e to the power of x will also going to approach to infinity. So ex plus 1 divided by ex minus 1 will be just infinity plus 1 divided by infinity minus 1. Now we all know that infinity plus 1 and infinity minus 1 are almost same, because if there's a number which is extremely large and you add 1 to it, it doesn't make a difference. Similarly, if we have that extremely large number and subtract 1 from it, it also doesn't make a difference. So in this case, the numerator and the denominator will just be almost equivalent, and that will lead us to a value of 1 being approaching. So from this statement, we can simply conclude that when x will be approaching to infinity, t, which is actually ex plus 1 divided by ex minus 1, will be approaching to 1. All right. So this is the thing. Now, 1 second. Okay. Now, our original integration from 0 to infinity of natural log of ex plus 1 divided by ex minus 1, which we were basically having, is now changes to integration from infinity to 1 of natural logarithm of t multiplied with 2 divided by 1 minus t square dt. All right. So now the integral which we need to solve is integration from 1 to infinity of natural log of t divided by t square minus 1 by 2. Now you will be thinking that how I have interchanged the limit. Actually, I have taken a negative sign out from this 1 minus t square term. All right, as I have taken one negative sign out, I had contemplated with this definite integral, which has switched the upper and the lower limit of this definite integral from infinity to 1 to 1 to infinity. And 1 minus t square is now t square minus 1, because I have taken a negative term extracted from it. The numerator 2 can simply be represented as a denominator of the denominator. It is a simple thing. Now, the integration which we need to solve is this. Integration from 1 to infinity of natural logarithm of t divided by t square minus 1 by 2 into dt. Now there's a theorem actually, and this is a very famous and a very nice theorem which every one of you who is listening to this video must be uh, concerned about, because this theorem can actually solve various problems of definite integration having a upper infinity limit or a lower minus infinity limit of any function associated with natural logarithm. This theorem is that it is when there's an integration from 1 to infinity of a natural logarithm of x divided by any function fx of dx, we can simply write it as minus of infinity, minus of integration from 0 to 1 of natural logarithm of x divided by x square multiplied with the function, in this time having the input as 1 divided by x into dx. Now, as I know that the person who will be watching this video are all mathematicians in a way, so you must be interested in the proof of this theorem, which I'll also provided. All right. I've used colorful pens in order to attract your attention. So here, let us suppose that x is equals to 1 by u. So when I'm going to differentiate both sides, it will be dx is equals to negative 1 by u square du. These are very simple calculus, which I'm basically doing. Derivating 1 by u with respect to u, it is just 1 minus 1 divided by u square du. And the persons who are watching this must be sure about it, that how to differentiate such simple algebraic expressions. So now, as x is approaching to 1, as we can see, u will also be approaching 1, because you can simply put x as 1 and can find the value of u. It will also be 1. And when x is approaching to infinity, then u will be approaching to 1 divided by infinity, which is actually 0. So when x is approaching to infinity, u will be approaching to 0. So our new integration will going to be with our adjusted integral limits. Our down limit will be 1 and our upper limit will turn to 0 from infinity, and natural log of x will be natural log of 1 by u, fx will be f of 1 by u, dx will be minus 1 by u squared du, as we have solved here. Now, rearranging these all things, it is from 1 to infinity. Natural log of 1 by u simply minus natural log of u by using the property of natural logarithm. Now this u square will going to take here u square f of 1 by u into minus of du. Now, using a property of definite integral, when I will going to extract a negative sign out from this definite integral sign, the lower and the upper limits will going to interchange their positions. So 1 to 0 will now going to be 0 to 1. So it will be now minus of integral from 0 to 1 of the function of natural log of negative u, or sorry, negative of natural log of u divided by u square multiplied with f of 1 by u into minus of du. So there are three minus signs. So obviously the resultant will also going to be a minus sign. So it will be minus of integration from 0 to 1 natural log of u divided by u square into f1 by u du. And we also know that in definite integral, we are free to change the variables. So I can just make u as x. So our variable is now changed to x, and we have arrived at expression like negative of integration from 0 to 1 natural log of x divided by x square of f of 1 by x dx. So I have proved this thing, that minus that integration from 1 to infinity of natural log of x divided by fx of dx can be now negative of integration from 0 to 1 natural log of x divided by x square multiplied with f of 1 by x dx. Okay, this is the thing which I need to prove, which I had proved. You can simply look to this page. Okay, take your time and pause the video if you are having any confusion. Now let us move further. I will going to use this theorem to solve this underboxed definite integral now, because this is the definite integral now we will be solving. Okay, so as this was the integration which we need to solve, I had applied that theorem. So this integration is now being converted as negative of integration from 0 to 1 of natural log of t divided by t square into bracket of 1 by t square minus 1 by 2 dt. Rearranging these things, you can simply end up here. Okay. I've just rearranged things, and you will going to end to negative of 2 integration from 0 to 1 natural log of t divided by 1 minus t square dt. Now, we all know that anything we all know that 1 divided by 1 minus t square can also be represented as infinite GP sum. Okay, from n is equals to 0 to infinity of t square to the power of n, because we all know that when we are having any expression in the form of like 1 divided by 1 minus p, we can write it as p to the power of uh, p to the power of 0 plus p to the power of 1 plus p to the power of 2, and so on up to infinity. Okay, the same I have done. In this case, t square is equals to p, so I have just used the summation thing here, summing up them from n is equals to 0 to infinity of t square to the power of n, which I've used as an infinite GP product here. All right. So now let us move further. Now I can now convert this integration. One second. Okay, now moving further, I can now convert my this integration as I'm having of negative 2 from integration from 0 to 1 natural log of t divided by 1 minus t square of dt by using this infinite GP sum to this minus 2 integration from 0 to 1 uh, sigma from n is equals to 0 to infinity summation from 0 to infinity of t to the power of 2n into natural log of t into dt. Now we all know that the variable n is actually independent from t, because we have used n just to represent the fact that I had now represented 1 minus t square to the power of negative 1 as an infinite GP sum. So it has no connection with t. So I can take this whole sigma term out from this definite integration, which I have done eventually in my next step. So I have negative 2 summation from n is equals to 0 to infinity of the function to be integrated from 0 to 1 of t to the power of 2n natural log of t into dt. Okay, let me clear my drawings first. Oh, no. Okay, so there's another theorem which we need to concentrate on. It says that when we are having any type of definite integral in the form from 0 to 1 of x to the power of m into natural log of x dx, we can simply write it as -1 divided by m plus 1 whole square. Now, again, we all are mathematicians, so it is our religion to show the proof, which I have done. Herein, we can basically have our natural log of x represented as u. Okay. And as we're having our natural log of x represented as u, I can make x represented as e to the power of u just by using the property of natural logarithms. Now I will going to differentiate both sides. I will going to differentiate x with respect to dx and eu with respect to u. So it will be like dx is equals to e to the power of u into du. And also, we need to establish our limits. Now I have taken natural log of x is equals to u, right? And x is from 0 to 1. So when x is approaching to 0, what will natural log of x will approach to? As we can see from the natural log graph, that when we are having natural log x here and x here, we all know that its graph is like this. Okay. As soon we are approaching to 0 from the left hand side, the graph of natural log of x is acting like an asymptote to the vertical line. Okay. So when x is actually approaching to 0, natural log of x will actually going to approach to minus infinity. And since natural log of x is equals to u, so u will going to approach to minus infinity, which I have here taken. This 0 is now being converted to minus infinity, and since natural log of 1 is 0, so obviously 1 will now going to change its limit to 0. And as x is now e to the power of u, so x to the power of m will be now e to the power of mu. Natural log of x is just u, dx is now e to the power of u du. Rearranging these terms, I will going to have our integration from minus infinity to 0, u multiplied with e to the power of m plus 1 u du. Okay, it is just a simple mathematics, which all you can do. Now the real thing comes. Now, what I have done here, as you can see, I have actually multiplied this whole thing with 1 divided by m plus 1 whole square. Now, to keep the things neutral, I need to multiply them again with m plus 1 whole square. All right. So what I have done is that I have taken one m plus 1 attached with this u. Okay. And I've taken that another m plus 1 attached with the derivative part of this here. Okay. So now as you can see that this is same as this, and this is same as this. So we can all take them as a same variable t. Okay. So it will going to be like 1 divided by m plus 1 whole square integration from minus infinity to 0 t into e to the power of t dt. And the limits of integration will also not going to change. It will still be minus infinity and 0 because m plus 1 is just a positive scalar quantity. Okay, it is just a positive scalar quantity. So when a positive scalar quantity is multiplied with negative infinity, it will still be negative infinity. And when it will be multiplied with 0, it will still going to be 0. Okay, so there will be no change in our limits of integration, and making m plus 1 u acting as an independent variable t again, I can represent this as like this integration from minus infinity to 0 t multiplied with e to the power of t dt. Now, when you are going to solve this by parts, you're going to get the answer -1. Okay, it is a very easy thing. It is a very easy thing to show. You just need to solve this integration by integrating by parts method. You will eventually going to get the answer -1. Okay. So I will not going to do that thing here because that will going to make the video lengthy, but it is easy for you to just solve by integration by parts, and you will eventually going to get the answer of this definite integration as -1. So multiplying this -1 with 1 divided by m plus 1 whole square, we will going to get our answer -1 divided by m plus 1 whole square. Okay, so I have proved this theorem, you fellow mathematicians. Oh my God. Now we can proceed further. Okay, now what we can do is here, what we can now do is that as we have proved this theorem, we can now change this integration using this. Now we can convert it like minus of 2, okay? Summation n is equal to 0 to infinity. Now this thing will going to uh, change in this form by using this theorem, okay? So it will be now like minus of 1 divided by, in this case 2n is m, okay? So it will be 2n plus 1 whole square. All right, so now you need to remember that what we need to solve, we just need to solve this expression. It is easy. We just need to solve this expression. This was going to be our answer. We just need to solve this thing. Okay, which I will going to do now. All right. Now, as we all know that now we need to solve this thing. This thing will now going to be our answer. As you can see that this is just the summation of inverse square of all the odd terms. Okay, so I can basically write this thing as this by summation of all the inverse square of the total numbers available and subtracting the summation of the inverse square of all the even numbers. By doing this, I can eventually going to get the summation of inverse square of all the odd numbers which this expression is representing. Okay, and we all know that this is the Riemann zero function evaluated at 2, subtracted with 1 divided by 4 of Riemann zero function evaluated at 2, because 1 by 2 whole square is 1 by 4. As you can see, I will going to take 1 by 2 to the power of 2 outside. This will going to become 1 by 4, and this will going to be 1 by n square left, which is just nothing but it is just the Riemann zero function evaluated at 2. So this thing is just 3 by 4 of the Riemann zero function evaluated at 2. And we all know that Riemann zero function evaluated at 2 is having a value of pi square by 6. Now, how Riemann zero function evaluated at 2 is equals to pi square by 6? Well, it has been shown by Pascal and Bernoulli. And you can simply watch a Mathologer video. Mathologer is a YouTube channel run by a very, very, very famous mathematician, George Paylam. You can simply visit Mathologer YouTube channel and can simply see the proof regarding how that Riemann zero function evaluated at 2 is equals to pi square divided by 6. So our answer will going to be 2 multiplied with this sequence, which is actually 3 by 4 of the Riemann zero function evaluated at 2, which is actually pi square by 6. As 3 into 2 is 6, canceling this and this out. Our answer is pi square by 4. So this is the complete solution of the definite integral question, which that guy was basically sending me. So this question is now completed. Thanks for watching. If you are watching this video, if you like my solution, then you can thumbs up a like, comment, but it is not necessary to subscribe, man. It's your choice. Okay. This was my first digital video. I was actually running a YouTube channel. I'm actually running a YouTube channel in which I'm solving mathematical questions. And this is actually my first video in which I have solved this using a share screen digital method. Because before this video, I was just solving questions in a whiteboard through a marker and posting with the help of my mobile and YouTube. And now I have taken a fucking innovation in my YouTube source, I can see. So see you in my next video.